So rule number one, junction rule. We've talked about this already. At a junction, whatever current flows in has to flow out. Current doesn't get created or destroyed at a junction, at these paths. Current is the same. So if there's a junction here and we have current flowing in and we have current flowing out, then we know that the sum of all the current in has to equal the sum of all the current out. I1 would have to equal I2 plus I3 in this case. Gesundheit. And then we have a loop rule. The loop rule says the sum of all the delta V's, all the potential rises and drops as you go around the loop, has to equal 0. Because potentials are like elevation changes on a hiking trail. So you could view your loop as a big hiking trail that comes back to the starting point, right? That makes a loop. You can view your current loop like a, I'll draw a little current loop here. So it's like a hiking trail. When you go through a battery like this, you are going up in voltage, right? If we started out at 0, let's just call the bottom of this battery 0 volts. We go through the battery, we come out at whatever it is, a 12-volt battery, we come out at plus 12 volts. We're now at sort of a higher elevation, right? We've gone up a flight of stairs or up a hill. When we go down through a resistor, we drop by a certain amount of potential, right? V equals IR for a resistor, so we can figure out what the potential drop is there. It's like going down a hill or down a flight of stairs. We're now at a lower elevation if we're on a hiking trail. We get through this one, we're at a lower elevation again. We walk back to where we started. If you go around a hiking trail, you get back to where you started, you better be at the same elevation again, right? Can't be at a different elevation. It's the same with potential. You go around that loop, some of these rises bring you up in potential, some of them are drops, they bring you down in potential, but if you go back to your starting point, you have to be back at the same potential again. Okay? So let's do an example, and I'll show you the best way to do this. So an example would be something like this. So take a look at this circuit. First thing when you see a circuit, see if you can reduce the resistors down using your parallel and series rules. Can you reduce this down any more than this? I don't think so. Because you've got this batteries, right? 2 and 3, you might think, oh, 2 and 3 are in parallel. But the tops of those are the same potential, but the bottoms are not, right? You'd have to go up by V2 to get to the bottom of R2 from the bottom of R3. So they are definitely at a different potential, different by V2. How about... and this is not in series with anything because there are junctions here and there. Yeah, so they're not, you can't make it any simpler using your series and parallel combinations, right? So this is as simple as it gets. So now we say, okay, let's use Kirchhoff's rules to solve this. So let's pretend we were given the three resistance values, R1, R2, and R3. And we were given the two battery values, V1 and V2. And if that's the case, then we have three unknowns that we're solving for. The current through R1, the current through R2, and the current through R3. So if we were given we would want to find the currents. So I'm going to walk you through in great detail the steps to solving the problem, because it's fairly simple to solve these circuit problems, but there are a lot of details. You have to just keep track of the details, take the time to set it up properly. Don't make shortcuts, and just get the right answer. Okay, so what's the first thing we do? We define a direction of the current in each branch. Just pick one. Guess. Doesn't matter. So R1, there's current that goes through R1. So there's a junction here, right, at the bottom. And whatever current goes to the left through the battery 1 and through R1, that's all the same, right? There are no forks in the road. There are no junctions after that. So this is all one current. This is one branch of our circuit. It's one current. I'm calling it I1. And what direction should we make it? Should we have it going with the battery, because that's maybe the way it's going? So we'll have it go this way. I1, which means it's coming this way, and it's going that way. I2. Should we have it going up? And then just to show you, let's see. Then we pick for I3. So if I1 is going to the left and I2 is going up, then what direction would I3 have to be going? To the right over here, or down through R3. But you can pick anything you want. You can pick up. Then you know for certain at least one of your arrows is wrong, right? If you picked I3 is also going in there, you know something isn't right? Something has to be wrong. So what would happen in the end, you would get a negative value for that current. And that tells you your arrow is going the wrong way. It's actually going the opposite direction. But it doesn't matter. Let's just have it go. I'm going to pick opposite what everyone would think, just to show you that it works in the end. All right. So we've done this. We've picked the direction of our current in each branch. It's just a guess. Sometimes maybe it's obvious what direction they're going. Sometimes it's not. There are circuits where the current goes backwards through a battery. You know what those circuits do to the battery? They charge them. If you have a rechargeable battery. If you don't have a rechargeable battery, maybe it causes a fire. If you have a rechargeable battery and you run a current backwards through the battery, that's how you get it to recharge. That's how you get the battery to charge. All right, so we've done step number one. We've chosen the direction of the current in each branch, and this is just a guess. So don't put a lot of thought into it.